The idea of a covering surface was introduced in the last programme when we looked at the locus of w squared equals z. This is part of the locus, the part over an annular region of the z-plane. Each point down here has 2 points vertically above it, corresponding to its 2 square roots. And that includes the points below the cut, because remember, these 2 edges have to be identified. So the locus is itself an annulus. Simply imagine unwinding and gluing the identified edges. Now forget about the locus idea for a moment and concentrate only on the correspondence between points up here and points down here. You can think of this correspondence as a 2-to-1 map, and we'll refer to it as the projection map from the top surface to the bottom one. We call the bottom surface the base surface, and the top one is a 2-sheeted covering surface. Actually, this name has a rather specialized meaning. It means more than just that the projection map is 2-to-1. It also means that the projection map is a local homeomorphism. That is, if you consider any point in the base and a small patch containing the point, then over the patch lie 2 homeomorphic patches containing the 2 corresponding points. That is, each of these 2 patches, considered separately, is projected homeomorphically onto the base patch. Let's look now at another example of a covering surface. Again, it's something you've met before in the programme on the projective plane. Remember the description of RP2 as the plane R2 plus the ideal points at infinity. In that same programme, we also showed a different model of the projective plane as the sphere S2 with antipodal points identified. That is, each point in RP2 is represented by a pair of identified points on the sphere. So a small patch on RP2 is represented by 2 identified patches on the sphere. Now think of this as an ordinary sphere without identifications. Then these rays through the centre define a 2-to-1 map from the sphere to the projective plane. And the map's a local homeomorphism because each little patch on the sphere maps homeomorphically onto a little patch on RP2. So the sphere is a 2-sheeted covering surface of the projective plane. Actually, both these examples are what we call regular 2-sheeted covering surfaces. You'll see later what we mean by irregular.
It's time now to look at the general definition of a regular covering surface. We have 2 surfaces, S tilde, the covering surface, and S, the base surface. And we have a map P from S tilde to S, the projection map. And for each little patch on the base surface, we have exactly n patches lying above it in the covering surface. More precisely, the map P is an n-to-1 map, which is a local homeomorphism. Notice this includes the case n equals 1, when the map is actually a homeomorphism. So n can be any integer greater than or equal to 1. We usually abbreviate all this by just writing the number n. So in our first example, we have an annulus A2 as a 2-sheeted cover of another annulus. Similarly, for our second example, we use this notation to denote that S2 is a 2-sheeted covering surface of RP2.
Actually, this example contains another example, because when we identify antipodal points on the sphere, then a belt round the equator represents a Möbius band. Remember, that's because each point is represented twice. So we can discard the front half of the cylinder, and the only remaining points to be identified are on the vertical edges. So we have to glue the edges with a half twist. And there's our Möbius band. Now, if we go back and consider the intact cylinder as an ordinary cylinder without identifications, then we have a cylinder, or annulus, A2, which we can think of as a two-sheeted covering surface for the Möbius band, because the rays through the cylinder define a 2-to-1 local homeomorphism onto the Möbius band.
So we've now seen 3 examples of covering surfaces, all of which are twofold covers, n equals 2. The question we aim to answer by the end of the program is what surfaces can be covering surfaces of what other surfaces? We'll find that given a base surface, there are a lot of restrictions on which surfaces could possibly cover it, and vice versa. To lead up to that, let's look at some more examples. If we look at these bottom 2 in a different way, we'll see a method of getting new examples with other surfaces and other values of n. For A2 double covering A2, instead of this picture, we can use polygons to represent the covering and base surfaces. That is, rectangles with opposite edges identified like this. Then what we do is think of the top rectangle as being made up of 2 rectangles stuck together. And we get the projection P by mapping each rectangle by the identity map E to the bottom rectangle. There's an important point to get clear about this approach. It might seem at first sight that the projection is not a local homeomorphism, because a patch like this looks as if it gets torn apart. But of course, it doesn't get torn when you take account of the identification in the base of the left and right edges. And we can do a similar trick on our other example. We represent the surfaces as rectangles. Then we think of the top one as being made up of 2 rectangles glued together. And this time, we map the first one identically, but we reflect the second one top to bottom.
That is, we turn the second one over. Now, Graham said that this polygon approach would lead to some new examples, but let me tidy up a couple of points before I go into that. First, let's check that this mapping is indeed a local homeomorphism. Continuity looks as if it might go wrong for points on this centre line. So let's take a patch containing such a point. For example, this one. The patch appears to get torn apart when you map down here. This half disk maps here, and this one maps down here when you turn this rectangle over. But in fact, the 2 diameters of these half disks are identified when you take account of the half twist down here. Actually, in both this example and in our first example, it's informative to look at what we've done in reverse, that is, starting with the base surface. What's really happened is that we've cut along this edge here, and we've taken 2 copies and glued appropriately to get the cover. And it's this idea of taking copies of the base which we can use to get some new examples. For instance, consider this second example, and take a third copy of the base. We have to take the final identification arrow downwards to extend the projection map to the third rectangle. In fact, we can simply use the identity map again. And the identifications on our covering surface mean that it's a Möbius band. So we've got a Möbius band as a 3-fold cover of itself.
In fact, we can repeatedly add copies of the base onto each of these 3 covers and get larger and larger values of n. You can look at that after the program if you like. But for now, we use these 3 as they stand to construct 3 new examples with a different cover and base, just by imposing more edge identifications. What we do is identify the top and bottom edges without twisting.
When we do that here, we get covering surface T2 and base T2.
So that's one new example, this one. And we can do the same for A2 covering M2.
Here we get covering surface T2 as before, but base K2, a Klein bottle.
So that's another example. And finally, when we identify top and bottom edges here, we get a Klein bottle as a threefold cover of a Klein bottle. Well, now that we've seen a lot of examples, let's ask our general question. Which surfaces can be covering surfaces of which other surfaces? Can any surface cover any other surface? For example, could we have any of these? Well, we can discard the first two straight away, because we can't have a local homeomorphism from a surface with a boundary to one without a boundary, or vice versa. What about these other three? Well, let's look at the classification theorem. We know any surface can be characterized by these three invariants. So the question to ask is, how do these invariants change when we pass from the cover to the base? I've already mentioned one result which helped us discard these two examples. If the cover has a boundary, so must the base, and vice versa. We don't go into the question of how many boundary components the cover and the base can have, because that's rather time-consuming. Instead, we'll move on to the first two invariants, and we'll prove a theorem about each invariant that tells us what the possibilities are for cover and base. Let's take orientability first. We've seen three types of example: orientable to orientable, orientable to non-orientable, and non-orientable to non-orientable. What about the fourth possibility, non-orientable to orientable, like these two? Well, we can prove this can't happen.
If the cover is non-orientable, the base must also be non-orientable. To prove this, take an orientation reversing curve in the cover. Then it's easy to show that the projection of this curve is also orientation reversing, and hence the base must also be non-orientable. The curve might get more complicated downstairs and might intersect itself like this several times. But that doesn't matter. The proof that it reverses orientation goes like this. Take overlapping patches in the cover which contain the orientation reversing curve and orient each patch, starting with this one and going round, making sure that at each stage the orientation in the overlap matches the previous orientation. Then, when you get all the way round, there must be a mismatch of orientations in the last overlap. Now project these patches onto the base and also project the orientations you've assigned up here. And because the projection is a local homeomorphism, then whenever the orientations match up here in the overlap of two patches, they'll match down here. And similarly for mismatches. Therefore, there's a mismatch here. So this is an orientation reversing curve, which proves that S is non-orientable.
So that rules out these two possibilities. But as you've seen, we can have the other way round, going from orientable to non-orientable. Now, what about T2 covering S2? Both surfaces are orientable. So theorem A doesn't say anything about this. But now look at Euler characteristic. The torus has characteristic 0, and the sphere has characteristic 2. Is this possible for a cover and base? Well, our theorem for Euler characteristic will show it's not possible.
Theorem B says that if we have an n-fold cover, then the Euler characteristic chi of the covering surface is n times the Euler characteristic of the base surface. To prove this, we merely triangulate the base, and for each triangle downstairs, we consider the points of S tilde that project to that triangle. And in this way, the triangulation of S lifts to a triangulation of S tilde which has n times as many vertices, edges, and faces. And that proves our theorem. Chi of S tilde equals n times chi of S. So what about the possibility of T2 covering S2? Well, their Euler characteristics make it impossible, because theorem B tells us that the Euler characteristic of a cover of S2 has to be 2n, which can't be 0 because n is greater than or equal to 1. In fact, consider the possibility of S2 being covered by any surface S tilde. Can we find any S tilde whose Euler characteristic satisfies our theorem? Well, an Euler characteristic of 2 is the maximum you can get, and only the sphere has chi equals 2. Therefore, the only possibility is n equals 1, and S tilde being itself a sphere, which is just the trivial covering of S2 by itself. In other words, we can't have S2 as a base of a non-trivial covering. For example, there's no surface which double covers the sphere. But wait a minute. In the last program, we did have a sphere double covering a sphere. The locus of w squared equals z was a sphere which double covered the z sphere.
Here's the locus in two halves, which have to be glued together along these spiral edges. And here's the z sphere. These two dotted edges are identified, and so are these two. So the whole locus is a sphere. You can imagine unwinding each half and gluing the dotted edges to see that each half is a disk. So it looks as if we've got a contradiction to theorem B. What's gone wrong? Well, this isn't a regular covering surface because of the two branch points at the bottom and at the top. Away from the branch points, it's a regular double cover, but the branch points make it irregular. How do our theorems work for covers such as this?
Well, theorem A is unaltered, and the proof's just the same. We just make sure that our curve misses all those bad points. But theorem B obviously goes wrong, or else we could not have that locus example. But it's easy to correct it. Triangulate S as before, but make sure that each point below a branch point is a vertex. Then the triangulation of S tilde that we get has n triangles over each triangle in S, and similarly for the edges and vertices, except for the vertices below the branch points. Each of these vertices has fewer than n vertices lying over it. So our theorem gets modified, like this. We subtract delta from the right-hand side, the total branch deficit. This is defined as follows. Whenever there's a branch point, look at the point in the base. Then there are q points over it, instead of n, where q is less than n, and n minus q is the deficit. If we add up all the deficits for all the points like this, and call it delta, then delta is exactly the amount by which we've overestimated chi of S tilde by taking n chi of S. And that proves theorem B dashed.
Let's see how this works out in the example of the locus w squared equals z. There are two branch points over z equals infinity and z equals naught. And over each of these, there is just one point of the locus instead of two. So each has deficit 1. So the total deficit is 2.
And this is correct because the base and cover are both S2, and n equals 2. So we get 2 on both sides. To end the program, let's use the modified theorem to actually identify the locus of an equation. This locus is a two-sheeted cover of the z sphere, except at z equals 1, 2, and 3, and possibly at z equals infinity. At 1, 2, and 3, the locus in fact has branch points, just like w squared equals z at z equals naught. And as before, the deficit at each branch point is 1. So we have a contribution of 3 so far to delta. Therefore, the Euler characteristic of the cover is either 1 or 0, depending on whether the deficit at infinity is either 0 or 1. The deficit will be 1 if there's a branch point over z equals infinity. And it'll be 0 if the locus is a regular double cover at infinity. But actually, there's a third possibility. There could be a pinch point at infinity. So which of the 3 possibilities is it? Well, we could use our algebraic trick of taking a new variable, z tilde equals 1 over z, and so on, but we can get the answers much more simply by using our theorems to study the 3 possibilities. Let's look first at the possibility that the locus is regular at z equals infinity. Then the deficit would be 0, and the Euler characteristic of the cover would be 1. But is that possible? Well, from theorem A, we know the cover has to be orientable, and it can't have a boundary because the base S2 hasn't got one. So we have an orientable surface without boundary, which we know must have an even Euler characteristic. So a characteristic of 1 is impossible. Therefore, S tilde is not regular at infinity. What about a pinch point there? In that case, the locus wouldn't be a surface. So at first sight, we can't use any of our results about covering surfaces. However, we can make a pinched locus into a surface by unpinching the locus. And the unpinched locus would be a perfectly good covering surface for the sphere. It would have branch points over 1, 2, 3, and it would be regular at infinity with deficit 0. But that's the case we've just eliminated. So the only possibility remaining is that we have a branch point over z equals infinity and deficit 1. So now we know what happens at infinity. We get a 4th branch point there. Now, what is the surface S tilde? Well, we already know its Euler characteristic. It's 0. And the only orientable surface without boundary which has Euler characteristic 0 is the torus. So we've finally concluded that our locus is a torus with 4 branch points. Well, that gives you an idea of how powerful our theorems are. Look what they've done for us in this particular example. We didn't have to use any tricky geometry, cutting or gluing bits of surface, in order to conclude that the cover was a torus. And before that, we showed there's a single point over infinity without using our algebraic trick. And furthermore, we didn't have to analyze a neighborhood of infinity to decide between a pinch and a branch point.